Assalamu alaikum dear students, I am Engineer Abdul Basit and we are in lecture number 24 of week 12. The topic we are going to discuss here today is the permeability of soil. Okay, so this is actually the new chapter we are getting in the that Baraja Imdaz book. Okay, so let's start the topic permeability of soil. Okay, first of all, what is permeability of soil? Simple. In all that soil samples, whether it is disturbed or undisturbed sample, so it may have some words left, and these words may be interconnected to each other. Okay, if these words are separated, are not interconnected, so then it has no use in the permeability. Okay, if these words that are present in the soil samples are interconnected with each other, so it will make a way to the soil to the water to pass through it. Okay, so when the soil or the water is placed or poured over that soil sample, so it will go through one word and then will go to that interconnected word, second interconnected word, and then to the third interconnected word, and then it will move through these words and will pass on through the soil sample. Okay, so these interconnected words are actually the reason for permeability of the soil. Okay, so now if we have interconnected words, soil is permeable. Now the soil, the water that is present in the soil will move from higher concentration to the lower, or you can say from higher energy to the lower energy. Okay, due to its own energy, potential energy, pressure, or etc, whatever that will be. Okay, so it will move through these words and will make its way clear. Okay, so the words are like interconnected with each other, but not that smoothly. Okay, so it will make that flow of water through these words, interconnected word, will make it a way for the water flow through it. Okay, so then the permeability will get enhanced with the passage of time. Okay, now uh, that permeability will lead to seepage as well, seepage of the soil, seepage through these soil samples. Okay, now for all the engineering properties, like for example you are designing a foundation of a building, of a bridge, let's say, of a building, let's say, of any structure, let's say. Okay, so you have to understand this permeability phenomena first of all. Okay, what this permeability phenomena say and what is the condition of the soil in that condition. Okay, and that particular area where you are going to design the foundations. Okay, so then it will affect the engineering properties as well. Okay, and it will affect the stability of the soil as well. Let's say you are building a dam structure from a soil and you are compacting it, so this is definitely a disturbed sample then, and soil is artificially compacted. Okay, then you will also investigate the seepage or the permeability through their soil. Okay, and you will then design accordingly. Okay, so this is what about permeability. Now let's say we have a soil that is totally consisting of larger particles, greater size particles, gravel particles. So through that soil, the permeability will be like of a higher value. Okay, like for example you can see in this sample these are gravels, and in 2 minutes the full tank of the water is passing through it. Okay, through this 1 meter sample. Okay, in 20 minutes it will be passing through that sand, because sand are fine particles, so in fine particles the words will be of smaller size. In gravel it will be of larger size, and it will be interconnected as well. In case of silt, the permeability will be comparatively lower. Okay, in case of clay it will be more lower, and it will take 2 days to make that water pass through that soil sample. Okay, so you can say as much fine soil particles you have in your sample, the more it will be difficult to for the water to pass through it. Okay, and the less will be the permeability and seepage. Okay, so you can say that clay particles are having the least permeability. Okay, and that can be used as impermeable material in the dam core as well. Okay, we'll talk about it later. Now coming to Bernoulli's equation, so this is like we don't have anything to do with this Bernoulli equation in the soil structures, but we are doing it for this hydraulic gradient phenomena. Here it is hydraulic gradient. Okay, so let me talk about this first. Hydraulic gradient is actually the ratio, or you can say the that ratio of the change in head to that original length. Okay, so if you have a soil sample, let's say this glass, let's say this glass is of fully contain that soil sample, and you have a disturbed soil sample placed in this soil, this glass, and this is having no bottom over here, and you are pouring some water in it. Okay, so definitely that water will pass through it. Okay, so here at this point the head of water will be of one value, and here the head will be changed and it will have another value. So the difference between the heads at this point and this point, that is delta H. Okay, and similarly the length from here to here is the L. Okay, so now the ratio of these two values will get us to the hydraulic gradient, and that is denoted by I, and this is hydraulic gradient. L is the distance between 2 points. Here in the next figure it is shown as well, in this figure. Let me this thing. Okay, this is already shown over here. So let us discuss that Bernoulli's equation, and then we'll gradually move to that hydraulic gradient again. Bernoulli's equation in hydraulics, fluid mechanics, okay, is simply like the total energy of the water while moving from one point to another will remain the same, and that total energy will be consisting of the potential energy or energy due to velocity, energy due to motion, and then the pressure energy or energy due to pressure, and that elevation, or you can say potential energy. Okay, or you can say or pronounce these things in the form of heads as well: potential head, kinetic head, and that pressure head. Okay, so these three types of energy or heads are making the total head of the soil sample. So the head of the soil sample at one point and at the other point will remain the same, but it may change from one form to another. Like at this point the pressure will be maximum, and at this point the maximum value we will have for velocity. Okay, so this will be interconvertible between each other, but the total head will remain the same at all these sections. Let me make it clear here. You can see that this is a pipe. We are talking in fluid mechanics now. Okay, we have a pipe. Okay, and water is flowing through this pipe, and it is having a diameter at this section, that is d1. So this is a larger diameter comparatively, and at this point we have a smaller comparative diameter. Okay, at this point the total energy, or you can say the total head, will be consisting of these three types of heads. Number one, we have pressure head. Here it is P1. This is that rho, that density of water, and this thing that G, it is gravitational acceleration, and this is V1. This is velocity at the first point. 2G, the first point mean at this section. Okay, then H is the potential head, or the height with respect to the datum. So here it is this green line is actually showing us the datum line. So the center of this point, this diameter is at a height h1. Okay, similarly at this point we will get again the pressure, the velocity head, and the potential head, that is elevation. So that is like at a distance, at a height h2 from the. Now this is that Bernoulli's equation. Simple. The head at the first point will be equal to the head at the second point. First point, second point. Okay, this dial installed at this point is giving us the pressure, and this dial installed at this point is giving us the pressure at the second point. Okay, the velocity at the first point is v1 and v2. So you can see that this is the sum of all the heads at first point, and this is the sum of all the heads at second point. Again I'm telling you, this is pressure head, this is velocity head, and this is potential head. Okay, now all these terms are like combination of something, that is H is the total head. Okay, here it is h1, h2, and this is not smaller, this is capital H. U is the pressure. Okay, here in the hydraulics you can say this is simply denoted by P as well. Okay, V is the velocity, but here it is in hydraulics it is denoted by capital V. Okay, and this is G, acceleration due to gravity, and R W is that gamma W is that unit weight of the water. Okay, so let's say we are talking about the water. So this is that hydraulics phenomena, or that is the fluid mechanics phenomena. Let us discuss the same thing in the form of soil. Okay, how we will do it? Let's say that same pipe or other pipe is filled with a soil sample. Okay, and that soil sample do have voids, and these voids may be interconnected to each other. Now if if the water is poured in that soil sample, it will pass through this soil sample due to gravity. Okay, as this soil sample is in inclined form, and this point is a bit at more head as compared to this one. Okay, so here the energy will be more potential energy as compared to this point, so the water will start to flow downward. Okay, now what will happen in open pipe, which is having nothing to resist the flow of water, will have the energy head, the kinetic energy head as well. Okay, there will be some energy of the flow of water because it is free to move. But in case of pipe filled with soil sample, it will be difficult for the water to move through it. Okay, it will definitely move, but it will be comparatively slower movement and slower velocity. Okay, so that small velocity is almost negligible in case of soil sample, but not in case of fluid mechanics where the pipe is empty. Okay, here the soil is like providing some resistance to the flow of water, although there are some voids and the water is flowing through it, but still the velocity is very slow and have giving us a very negligible value. Okay, so that can be neglected. So if you neglect the velocity, so definitely this thing is zero, this thing will become zero, this thing will become zero. So if it is becoming zero, then this whole term will become zero. Okay, so talking about their soil sample, you will see this whole term is equal to zero. Straight away talking about soil mechanics. So this is like this term will become zero. You will get only this u divided by gamma w and this z. Okay, don't get confused here that this equation is different from this one. This is for fluid mechanics phenomena. Okay, we are not talking about fluid mechanics, just we are using the Bernoulli equation of the fluid mechanics over here. Okay, so this is for clarity. For soil mechanics you will use this equation. Okay, so it must be clear to you people. And then u is pressure, this is unit weight of water, this is velocity, which is equal to 0. So 0 divided by anything is 0, this term will become equal to 0, and this is that elevation head. Okay, now here you will see that all the terms are explained over here. Now if that velocity head becomes 0, so this will be the equation for the head at one point. Okay, at the first point, that is u divided by, you can say this is pressure head and this is elevation head or potential energy head, but no velocity head, no kinetic energy head, because velocity is equal to 0. So this is, I hope this is clear to you people. Now again, if we consider this soil sample and we take 2 points, this is the first point, this is second point, this point is like a point, this is point B. Okay, so let me explain this graph first, this figure first. This is a pipe which is having soil sample in this blue color dotted form. Okay, so this is a soil sample filled in the pipe. Okay, we have 2 points. At point A we have installed a piezometer. Okay, here at this point we have installed a piezometer. I hope you do understand what is piezometer used to. This is actually used for the determination of head of water at this point and determination of head of water at this point. Okay, now at this A point, you can see this is their dotted line is actually at a height ZA from the datum. This is datum line. Okay, so this is at height A from the Z. Let me plot it. Let me plot it. Okay, here it is. You can see this point is actually ZA. Okay, this is A point. Okay, this is B point. Okay, and this is their datum line. Okay, now at this point the head is actually, like you can see in this piezometer, the water is raised up to this level. So against the datum, this is HA. So this is the pressure of water at this point, which is being determined by piezometer, with the help of piezometer. And at this point you will see the piezometer is giving us a bit lower height, and that is at this point, and with respect to the datum, this is HB, which is from this point to this point. Okay, now ZB. ZB is that elevation of this point with respect to the datum, which is ZB. You can say this is potential energy head. Okay, now the that pressure energy head, that will be U8 at this point divided by gamma. So this is the pressure energy head, and the total head will be equal to this thing. So you can say HA will be equal to this thing plus this thing. Okay, and similarly HB, this HB will be equal to the sum of this and this. This is pressure head, this is elevation. So I hope this is clear to you. What is delta H? This is the change in heads, as I told you earlier about hydraulic gradient. Okay, so the nominator of the hydraulic gradient is the change in head, which is delta H. So how to calculate it? Delta H will be equal to HA minus HB. Simple. Okay, so this equation will be like possible in this form because there is no velocities to consider. Okay, now talking about L, this is L, the length between these this A point and B point, this is L. Okay, now moving on, let me make it clear first. Okay, here it is. You can see the delta H, change in head, will be equal to HA minus HB. Already I told you, HA, this is HA, this is HB. The difference of these two is delta H. So here it is. Now at HA, the head will be equal to, the total head will be the sum of the pressure head and potential head. So this is A and A because it is point A. Now at point B, so on. Minus is the requirement of this equation, already put it here. Okay, so now you will calculate whatever the value is, then you will use that value over here. Okay, and L, straight away, this is L. Okay, this is the length, so you can say this L, this is L. Okay, now you will use it in this equation and you will get the delta H, and you will use the L over here. Then delta H divided by L is the hydraulic gradient. This is actually the need of soil mechanics, not hydraulics. Okay, we are not talking about that fluid mechanics phenomena. Fluid mechanics, we do have the hydraulic gradient over there as well, but we are not talking about fluid mechanics, we are talking about soil mechanics. So this is something very important for us. Okay, now how? Let's make it clear. Hydraulic gradient, let us draw a graph between the hydraulic gradient and velocity, or you can say we should draw a relation between velocity and hydraulic gradient. Okay, so initially when the hydraulic gradient is increasing, at the same time the velocity will also be increasing. You can say there will be a direct relationship between velocity and hydraulic gradient, and it will give us a straight curve. Okay, a direct relationship which shows us the laminar zone. So this rectangular triangular portion, this portion between these lines, this is giving us the laminar zone. What does it mean by laminar zone? Here the soil, the permeability of soil, or the water that is passing through that soil, or the seepage happening through the soil, will be laminar. That flow will be laminar. That particles of the soil will not cross each other. So this is laminar zone. Okay, then transition zone is like moving from laminar to turbulent, so in between that zone is called transition zone. In transition zone, what will happen when the hydraulic gradient is continuously increasing? So after some a specific limit, what will happen? That hydraulic gradient, where the further increase in hydraulic gradient will lead us to a smaller increase in that velocity. Okay, so this will not be a direct relationship like it is expected. Okay, this arrow is showing us that expected relationship, but it is not like that. It is giving us a curved portion where the hydraulic gradient value is comparatively more as compared to with respect to that velocity. Okay, so velocity is less as compared to hydraulic gradient increase. Okay, so then this will give us this inclined portion, or you can say this circular portion, curved portion, and further increase in hydraulic gradient after this point will lead us to a curve that is very much flat. Okay, and after that you will see that this is a turbulent zone. Okay, and turbulent zone will start and so on. So you can say that the soil may have three types of flow due to seepage. That may be laminar flow due to seepage. Transition zone may occur between the turbulent and the transition, and may be turbulent. But in case of soil, we consider it is only laminar, not turbulency. Okay, so then we can say that velocity have a direct relationship with the hydraulic gradient. Okay, so we consider in case of soils there is no turbulent situation, only laminar situation. So this is ideal situation. Practically it is not happening like that. All the flows almost are turbulent. Okay, here we are considering laminar flow for our ease for further calculations. Okay, so this will be the equation. Then the velocity is directly proportional to hydraulic gradient for laminar flow. Okay, in fractured rocks, sometime when we are considering the water flow or the seepage through fractured rocks or stones or gravels, okay, are very coarse sand, so it will be considered that terminal flow condition is existed over here, and this equation is not satisfied. Okay, so if this is not satisfied, then we will work on further on this topic, and we will derive the Dale's equation and then so on, and then we will derive what to do with the turbulent case. Okay, initially our idealization is this is only the laminar case in the seepage of soil. Okay, so I hope this is clear. In the next lecture, inshallah, we will talk about the Dale's equation and hydraulic conductivity. So here it is, there are some images of that. Okay, so thank you very much for listening. Assalamu alaikum.